In the next part, we will first construct the mapping, so the F function, for the neural networks, and later on we will see how to train it, how to do the learning. First, we have to study what's called the basic perceptron model, which is simply the same thing as a logistic regression model, but we will write it in the jargon of neural networks. So, on the left-hand side here, graphically, I have what's the feature values, x, and I will call them as the inputs here. Then I have the parameters of my model, which will be this W matrix and the B scalar. And the output is again the same, fx given theta. Now, in this case, the parameters of the model theta are simply the W matrix and B. Now, how do I use this W matrix and B on the inputs? It's given right here. It's basically a model of binary classification with logistic regression. I have x here, which has, let's say, some certain dimensions. I multiply it with W matrix and then add a bias to it, so the B value. And then I basically change this linear function into a probability using a nonlinear function as we've seen before. So the output, again, is a probability of belonging to a certain class. Now, this function, we will actually study it in two different parts. One of them is the activation. The activation is the inside the nonlinearity, or in a sense, the linear part. So the activation is the weights times x, my input, plus the bias b. The second part is a nonlinearity, which actually converts the activation into a probability. And I will call it the sigma. And we've seen already sigmoid, and we will see another thing later on as well. Oh, sorry, let me get my mouse back again. There we are. Now, the activation, what does it do? So it's actually a linear transformation of the features. And we've seen this before with the logistic regression. Now, if I actually have d dimensions in my features, so d number of features in my feature vector, then I will have d plus 1 number of parameters. I will have first my W matrix will be 1 times d, so one weight for each feature. And then I will have this bias as well, so that will be d plus 1 number of parameters. We could also write this in terms of homogeneous coordinates without any difference. What does this function do? Let's look at a very simple example where we have two features, x1 and x2. Now, this actually comes into this x vector. If I actually multiply these features with different w's, what I do is I basically pick different lines in this 2D space and simply project all these samples onto that line. For example, one transformation can give us this projection. What I show here is I first draw a line, in this case, this line right here, and then I basically map all these points onto this line and look at the histogram. And I see that in this histogram, the red dots and the blue dots are well separated. If I look at another transformation, so that would be another line on this feature space, I would, for example, get such a histogram from the projected samples. And here, for example, you see that they're less well separated. Now, that's the role of the W matrix. W of the B is simply put the bias into it, meaning that, so where should I actually use the threshold to separate between the two classes? The nonlinearity, on the other hand, as we've said, in these cases maps the real line from negative infinity to positive infinity to probabilities, to something between 0 and 1. And we've already seen the sigmoid function right here. So it was basically taking the activation and 1 over 1 plus exponential of the negative activation. And the sigmoid function is shown with the blue curve here. But you can also think about other nonlinearities, for example, the hyperbolic tangent function, which is given like this, and which basically serves the similar purpose. The function itself is slightly different. It has a different profile, but it also maps negative infinity to positive infinity to between 0 and 1. And here the activation, when it's one-dimensional, it's very obvious, so I basically use the activation function on dimension. But when my output is multiple dimensions, for example, if I have multiple labels, then the activation function, or the nonlinearity function, is applied in an element-wise manner. So if I have three y's, y1, y2, y3, I simply apply the nonlinearity to each component independently. Now, given the model, we've already seen it a little bit. So in the logistic regression, for example, given the samples, we could visualize the model by simply drawing the decision boundary. So let's do it again. So this decision boundary, this line, separates the classes, and it happens to be the line where my model predicts probability of belonging to a certain class 1 equals to 0.5. So that's the line where my model is completely uncertain what the sample, which class the sample should belong to. Anything above, it will assign it to a certain class. Anything below, it will assign it to another class. Now, these samples are kind of well separated. You see that there are some samples where my model makes an error, but overall, for most of the samples, they're well separated with this decision boundary. If I actually look at a data set that's a little bit more complicated, I can still apply it, and I can basically find decision boundary. However, this time you'll see that actually the model makes more errors. You see that here, for instance, there are more red points that remains in the boundary, under the boundary, and there are blue points that remains above the boundary. So that's also fine, because sometimes the model itself, or the data samples itself, are quite complicated, and we cannot really find a model that can well separate them. So this is a very specific example where actually any model will have a difficult time. But there are certain cases where actually it's clear that we don't only need a linear model, but we need more complicated model. Let's take this example. So I have two sets of samples again, two classes, the blues and the reds, and I have two features. And as a human, we can already draw a decision boundary that can well separate these two classes. The decision boundary goes something like this. And then it will take a turn there and then cut from here. Now, the logistic regression, or the perceptron model, is a linear model. So when I actually train the model for these samples, or find the best parameters for these samples, and draw the decision boundary, what I will get is something like this. So again, the model does as good as it can do. So it actually well separates the blue points from the red points, but it can actually do a little bit better, as you can notice here. So, some notes on the perceptron model. Logistic regression is the building block of the perceptron model that we've seen. And it's essentially a linear model. So, for example, the decision boundaries that it can actually construct are linear in nature. And it cannot model more complicated separations. Well, the important part of the perceptron model, although it looks like it cannot do much because it cannot separate complicated samples, complicated data, it's actually the building block for building more complicated models, which will be able to separate such complex data. Now, we have not seen how to train it yet, but as I said, we will first focus on defining the mapping, the f function, and then we will talk about how to train the parameters. Before going that, as I said, let's see how we can actually create more complicated mappings, more complicated models. So our goal really will be, when we see this data, we really want a model that can create this decision boundary, which, as you can see, it's similar to what, as a human, we would have drawn for these samples. So how do you achieve this? The idea actually is quite simple to explain. So first, let's create a simple graphical representation of this, so I don't have to draw these circles all the time. So the perceptron model has these x inputs, the parameters, and the output. I will represent this perceptron model simply with this bar, the arrow, and the output here. Given this simple graphical representation, I can quickly create a multi-layer perceptron model. Simply add certain layers. And the idea is very simple. So I start from this guy, where I know that the function model itself is given as the nonlinearity and the activation side. I simply add another layer, a hidden layer inside between the input and the output. And I already have a more complicated model. It's a multi-layer perceptron model. Now, the function for this architecture, or for this neural network, is written like this. So first, I have the first layer that basically takes the inputs x and multiplies with certain weights and adds the bias, feeds it through the nonlinearity, and repeats exactly the same thing now with the following layer. So this and this transition are mathematically same objects with different parameters. In the first one, I basically have W1 and B1. And in the second one, I have W2 and B2. So this transition itself acts on the input, and this transition acts on the hidden layer, or the output of this first transition. So it's really a concatenation of functions. I first have the F1, that's the first layer's transition, and then the F2, that's the second layer's transition to the output. So the parameters, well, when I add these two transitions, or if I add this hidden layer, instead of having one set of parameters, I have two sets of parameters. I have θ1 and θ2. If we write them out, they will simply be the weights of these transitions and the biases. Now, this model itself is actually able to do the nonlinear separation that we were after. So again, I'm putting down the samples that we've seen before, where the linear separation did as good as it could, but it couldn't separate the samples really nicely. By just adding a hidden layer, a new one, I'm able to now separate the boundaries quite nicely. So I'm actually creating a decision boundary that is more accurate than the one here. Now, the power of the multivariate perceptron model is it's more flexible than the perceptron model. So this guy, as you can imagine, is more flexible than this. That means it can actually create these nonlinear separations when needed. Well, when the data is really linearly separable, it can also do what the perceptron model can do. So it can actually do linear separations too. Okay, so that's the concept, but there are several details that we need to cover. So when we actually created this hidden layer, we don't really know how wide it should be, meaning that what is the dimension of this hidden layer? So the dimension of the feature is set, that's kind of the dimensions of my input. And in this case, the dimension of the output is 1. So I'm actually interested in the binary classification, for instance. But here the dimension, well, that's actually a model choice. That's really a design choice that the user will make. And we'll represent it with D1, and that's the width of the hidden layer. Mathematically, what this corresponds to is that my first transition from my input to the hidden layer is represented by this W1 matrix, right? So that actually transforms the D-dimensional input into a D1 dimensional hidden layer. So when I actually do this operation, so x times W1, this will be D1 dimensional. And then I add a scalar, which means adding a scalar to all the dimensions, adding the same scalar to all dimensions. And then going through the nonlinearity, so element-wise application of the nonlinear function, this itself will now be D1 dimensions. In this case, W2, which is the transition from the hidden layer to the output, will be 1 times D1. So the output itself will be only one dimension. So the width of this layer, the D1, is really a design choice. And it has huge effects on what decision boundaries a model can create. So if I keep it very simple, for example, D1 equals to 1, so one-dimensional layer, I see that actually my model is not able to separate these samples at all. Now, if I use D1 equals to 2, so I have two-dimensional input, two-dimensional hidden layer, and then I go to the activation, I already see that I can create nonlinear decision boundaries. I can actually use more complicated models, so increase D1 to 3 or even to 5, and we see that as we now start increasing the decision boundary, the width of the hidden layer, I'm able to create even more complex decision boundaries. So my model becomes even more flexible. Now, maybe this example is not very illustrative of what's coming, but let's look at this guy here. So here, my data is quite complex. I see that actually one class is surrounded by the other class in the feature space. So when I use D1 equals to 1, again, I'm unable to solve this problem. If I use D1 equals to 2, I create a nonlinear decision boundary, but I also see that, well, it's not exactly very good. I don't separate them well enough. But if I use D1 equals to 3, then I see that actually my model is able to really separate the two classes, creating this circular boundary, which is quite nonlinear. Some notes on the width. So when D1 equals to D, notice that I only create a nonlinear transformation. So basically, I take the features, I first apply a linear map, and then do nonlinearity, and then apply another linear map, and do a nonlinearity, and so on. When D1 is larger than D, so the width of my hidden layer is larger than the dimensions of my input, then I take the input and I map it to a higher dimensional space. And there, it actually often becomes much easier to separate classes in higher dimensions. You're able to model much more complicated decision boundaries, and the cost of that is you will have larger number of model parameters. But as we've seen in the previous example, separating these classes only became possible when we mapped two-dimensional input space to 3 dimensions. When D1 is smaller than D, so the size of the hidden layer is actually smaller than the size of the input, that basically means there's a compression, there's an information bottleneck. So there's a possible loss of information. So this becomes interesting for determining, for instance, low-dimensional representations. Remember PCA? We will talk about it again at the very end of this lecture, not today, but the end of the entire course. But this only becomes interesting in those cases. Well, not only, but this becomes interesting on those cases. So that was the width. But notice that there's another dimension that we can actually change a multilayer perceptron. Here we added only one hidden layer, but we can in theory add many hidden layers. Remember, it's basically, I take the input, I apply an operation, that basically gives me a hidden layer, and I apply a similar operation, and I can repeat it many, many times. So in this case, I had 2 layers, so really F1 and F2. But if I take basically another description, say that, okay, the hidden layers actually is the output of a hidden layer is actually given by a nonlinearity and a linear map of the previous hidden layer. Then first, I can write the hidden layers in terms of a new function view. So my input, my 0th hidden layer, is my input space. And my second hidden layer is simply, it can be given by the f of my input, so that's my output. So the function view, then this can be, the output can be written as h2, which is given as f2 applied to f1 applied to x. So in this view, you can see that, well, L can be anything. So instead of one hidden layer, I can actually add many hidden layers in the same network. So again, it will be the same thing. H0, my 0th hidden layer, can be viewed as the input. And my last hidden layer, or my output, can be viewed as the last layer of my network. I'm using the hidden layers, but sorry, these are with the 0th layer and the alt layer. So 0th layer is the input and alt layer is the output. And anything between are the hidden layers. From the function view, I basically do exactly the same thing. So each transition here takes the activations of takes the values of the previous hidden layer, computes a linear transformation, feeds it to a nonlinear function to get the output, which is basically the values of the next layer. So the entire mapping can be written as a composition of all the different layers. So FL composed with FL minus 1, so on, and F2 composed with F1, which is applied on X. Remember, each of these transitions is basically a linear transformation and then a nonlinearity. And each of these linear transformation has the matrix WL and the BL. So if I want to now look at the parameters of this more complex model, it's simply concatenation of all the parameters of all the layers. So theta L minus 1 until theta 1. And they are the weights and the biases of these transitions. So what is the effect of the depth on the decision boundary? So let's look at the complicated data here. I have 2 classes again in the 2-dimensional feature space, and I can see that their separation is quite difficult. So they're actually somehow in between. Now, if I don't use any hidden layer, I basically use a simple perceptron model. I can only model a linear separation, so I'm not able to really classify or separate these 2 sample sets. If I only use one single hidden layer, I'm already do quite an interesting thing. I see that I create the nonlinear decision boundary, and I'm able to well separate the two classes from each other. So even adding one single hidden layer, so creating the multi-layered perceptron model that we've seen before with only one orange bar in between, we're able to create nonlinear decision boundary. And if we actually add the more hidden layers, now we're able to create even more complex decision boundaries and better separate these samples. So some notes. So no hidden layer basically means a logistic regression model, so it's a linear decision boundary or linear model itself. When I increase the depth, I allow more complicated models, and that leads to a larger number of model parameters. So in theory, it needs more samples to fit reliably. On the better side, it's really able to separate boundaries quite well. Now, it may also become more difficult to train than a linear model because it has multiple parameters. So you might ask, we've seen the depth and we've seen the width of a network. So you can ask, so what is the interaction between depth and width? Let's take an example and we'll look at the same data that we've seen in the previous slides. So now we know that we can actually apply a single hidden layer with width 2 to this data set, and we're able to separate these two classes with a nonlinear decision boundary. We can actually increase the number of hidden layers, but keeping the width of each hidden layer to 2, and we're able to get the decision boundary. So what happens, for example, if we use another width? Let's assume that we actually use a single hidden layer, but width equals to 3. And we see that this also creates a nonlinear decision boundary, much more complicated than the one here where we use width equal to 2. It's also very different than the one given here. So we see that actually width makes a model, increasing the width of a network makes the model more complex. Increasing the depth of a network also makes the model more complex. So it's actually both at the disposal of the user or disposal of the designer using width and depth and their interaction to basically create complicated models that can actually solve complicated problems. Now, the interaction between the depth and the width is complicated. Both allow modeling more complicated class separations. The choices are basically the architectural design choices. So there's no widely accepted method for automatically determining an architecture for a given problem. It's really problem specific, and most of the time it's based on trial and error based strategies. So it's kind of an engineering intuition art. And the most principled way of doing it is basically having two different data sets, so one training set and one validation set, where I have also the labels of a different set of samples, and I try different architectures and simply compute the error on the validation set and choose the best one. That said, there's quite a bit of theoretical work on trying to understand the effect of width and effect of depth. For example, there's some work saying that if you actually increase the depth, then you become invariant to nonlinear transformations in the input space. And if you increase depth, if you increase the width of a network, you basically increase the capacity of the network in terms of the information that flows through it. But we will not go into the theoretical details here. Now, the nonlinearity itself is also an interesting topic, and we've seen the sigmoid and the hyperbolic tangent before, and their role was really to transform a continuous space, a real line from negative infinity to positive infinity, and map it to a probability between 0 and 1. But realize that in an intermediate layer, in a hidden layer, you don't really need to have probability as outputs. Actually, you can use many different nonlinear functions. The only thing you want is a nonlinearity. And it's also an element-wise application. And people figured out that actually to basically have better models, better in the sense that they're actually trainable easily, using a different set of activation functions or nonlinear functions in the intermediate layers is more useful. And a couple of these functions, probably the most popular one, is what's called the rectified linear unit. So it's a linear function whenever the activation is larger than 0, and it's 0 whenever the activation is smaller than 0. And then there are some variations on it. For example, leaky ReLU that again takes a linear model when the activation is above 0, but when the activation is below 0, it also takes a linear model, but with a different slope. Or you can actually think of a continuous or a smooth version of this with the exponential linear unit that, again, takes a linear model whenever the activation is larger than 0. And actually, when the activation is smaller than 0, takes an exponential form to decrease gracefully. And at the junction here, the model itself remains smooth. So some notes on nonlinear functions. The main difference between nonlinear functions is their derivatives, really. So the sigmoid and the hyperbolic tangent saturate for high values, and their derivatives diminish. If I look at these functions, I see that if I take the derivatives of these functions here or here, they're very close to 0. However, the other functions, the ReLU, leaky ReLU, and exponential linear unit, has derivative equals to 1 whenever the activation is larger than 0. And this becomes very interesting for the training. We will see actually when we talk about backpropagation that non-diminishing derivatives is actually quite useful. So the ReLU has a constant derivative of positive values, and it doesn't saturate for positive values at all. ELU, leaky ReLU, parametric ReLU are all variations on the same idea. And from a theoretical point of view, the rectified linear unit is actually the activation of infinite number of binary sigmoid nodes, all combined together. Now, both ReLU, ELU, and leaky ReLU yield really good performances when we actually create deep neural networks with multiple layers to solve complex tasks. Now, I want to basically talk about what the feature view of the multilayered perceptron is. So, one of the interesting parts of neural networks or deep learning is that it's able to extract features from data itself. So what does it exactly mean? That means, from this point of view, is that here at the very, very final layer, notice that if I forget what's coming here, at this layer, I simply have a logistic regression model. So that's kind of a linear model at the very end. That's a perceptron model. So I can actually consider this entire network as this part that's actually under this blue rectangle as the feature extractor. It simply takes the inputs and transforms these inputs with these linear transformations followed by nonlinearities through the hidden layers. And when it comes here, I basically don't have the inputs features, but I have a transformed version of those features in a nonlinear manner. So mathematically, at the very final layer, right here, I have this phi of x. Now, this is a nonlinear transformation of the input. Basically, the network itself then simply creates a different representation of my input. And that's a representation that I can actually successfully separate with a linear classification model. So the feature map phi x that maps D to the dimension of the final layer is an automatically determined nonlinear feature mapping, which, if I talk about the binary classification problem, its aim is really to, at this point, create a representation of the data that's linearly separable. So I have the linear classification at the end, I have the feature extraction here. One important point to mention is probably the value of the nonlinear functions. So why do we actually use nonlinear functions to basically change a linear transformation? So what happens if all our activations were just simply linear functions? So instead of having a nonlinearity, we simply have a linear function again. Well, what happens in this case? So let's write it out. Our activation was basically given by a linear transformation itself. So if I write the function or the output of the layer L, given the layer, the hidden layer or the layer L minus 1, now the activation is basically multiplied by another matrix and added another bias. Effectively, in this case, the entire layer can be written by another linear function. Okay, now if I compose multiple layers, so create a very deep neural network with multiple layers, I see that effectively, I just create a very big linear map. So this is simply the same thing as a single model. So basically, a single layer model, such as a logistic regression. So if I don't use nonlinearities in my neural network, effectively, I create a very complex model that simply does just a linear separation. So the nonlinearity is actually extremely important to be able to create models that can separate complicated data. Now, so far we've only talked about binary classification, but the same concept can be applied quite simply to multi-label classification as well. Instead of having one output, I will simply have multiple outputs. And nothing really changes. It's just the dimension of the output layer. So the last layer of the network is now constructed to not perform binary classification, multi-class classification. And it's kind of common to not use any nonlinear activation function in the final layer, but converts into a nonlinearity afterwards. So in the binary classification, I had this function. My final layer activation was actually fed into a nonlinear function, for example, a sigmoid function, to convert the real line into a probability. So this was the probability of belonging to class 1, and if I'm interested in probability of belonging to class 0, I simply I take 1 minus the probability and get the probability of belonging to the other class. In the multi-label classification, things are a little bit different. As I said, at the output, now I have, if I'm looking into a k-class classification problem, at the output, my activation is actually k-dimensional. And all of these are basically continuous values. You see, these are linear maps. So I basically have to convert k continuous values into a set of probabilities whose sum will be 1. And for this, I use what's called the soft max nonlinearity, which is given in this form. So to be able to compute the probability of a sample belonging to the class K, I simply take the activation, the kth component of the final activation, takes the exponential of it, and divide it by the sum of all the other exponentials. Now, this softmax function converts all these functions, all these activation values, to between 0 and 1, as you can see from this ratio. Moreover, if I sum over all the other probabilities, it's guaranteed to be to sum up to 1. So that's actually a real set of probabilities. When I use, when I'm trying to solve regression problems with neural networks, well, things don't change that much. Regression network is very similar to a classification network. If I'm looking at a m-dimensional regression output, I basically use exactly the same network. This time I output again just m values, but I don't have to feed them through a nonlinearity function such as the softmax. I simply can read off the values. And it's again common to not use any nonlinearity activations at the final layer. So the regression problem, if I, for example, have this data set, so my model underneath is really this model with the red dashed curve, and using this ground truth model, I generate samples, training data, basically by sampling the curve here and adding some noise, and the data that I see are these blue points, and I can try fitting several neural networks to these training samples. For example, I can try 4 different neural networks that will basically give me these fitted models. So I try, for example, a neural network with only one hidden layer, and in the hidden layer there is only one, the width of the hidden layer is only 1. I can try another one with, again, one hidden layer, and the width of the hidden layer is 2. Here I try a neural network with 2 hidden layers, width of each hidden layer is 2, and finally a neural network with hidden layer that has only one hidden layer, and the width of the hidden layer is 3. And I see that all these neural networks behave slightly differently. So I see that the lowest complex, the simplest neural network, doesn't really able to match the data, while the other ones actually match the data quite well. I actually see that when the neural network is very complex, meaning that there are multiple hidden layers, I see that actually it's able to really match the data, but perhaps fits a little bit noisier, while the other ones, the green and the yellow curves, are able to very well fit the data. So actually, it's able to solve the regression task quite nicely. One point to ask here is, well, we're only here looking at the feature space, or the part of the feature space where we have examples. So in a sense, these curves simply interpolate between the observed examples. One natural question to ask is, can it actually extrapolate to areas where we have no examples? So we can actually look at that right here. So what I draw here, I simply zoom out in a sense. And underneath, I show you the real function that I used to create the samples. And then I evaluate all the neural networks for feature values that are actually outside in the range of the samples that I see. So in the same range as my real function, the ground truth function. What I see here is actually all of the neural networks, they deviate from the real function. So they're not able to actually determine the real function that I use to generate the samples. So in a sense, if the function is the reality, if the red dashed curve is the reality, none of these neural networks is able to determine it. None of them is able to extrapolate in the feature space where no samples were seen. But that's normal because actually these samples could have been created by any of these models. They're all likely, they're all equally likely. So it wouldn't be able to really find this function specifically. If I'm actually interested in methods that are really able to find this function, then I really need to integrate more information into the model, saying that I'm actually only interested in the sinusoidal function. So find me a sinusoidal function that's able to fit these sample points. And that's extra information. So blindly fitting neural networks to the data will give you the ability to interpolate in the areas where you see samples. But the extrapolation capabilities will be always questionable unless you also integrate some knowledge about the physical system. So in a sense, you can see that actually data-driven approach, like the one we take here with the machine learning approach, might not be able to solve this problem. So we really still need information about the physics. So some notes on prediction extrapolation. So fully connected neural networks are very powerful generic models that can represent very complicated functions. It is important to choose the network architecture correctly for best prediction accuracy. We've seen that if we choose it incorrectly, we might actually end up with very simple models that are not able to separate complex boundaries. And if we also select very complicated models, then we see that it actually behaves a bit odd in the areas we want, in the areas that we're interested in. For example, in this case here, the model acts a little bit odd unexpectedly in this regime. That's because probably the model is too complex. How to choose a network architecture is a very good question. The most principled way is to do it in a validation set. The models can interpolate between samples, as we've seen, and they're actually quite good in interpolating. However, they do not extrapolate well in general. That requires really knowledge about the underlying system. And lastly, what we've seen here is feed-forward network architectures, which basically means that I give the input X here, and I simply feed it through the hidden layers until it reaches the output, until I evaluate the function. So the function evaluation, in a sense, is feeding the input forward into the network. So the flow of information is forward when I'm doing predictions. That kind of ends the construction of the mapping, and next we will see how to train these neural networks.